So let us go for the last test on the second model, that is the retardation test. Okay, while coming for the retardation test, so this is how the circuit diagram will be represented. So considering a DC supply, so positive and negative supply, the field will be separately connected and the armature will be separately connected to the DC supply. And here we are considering one SP DPST switch, DP DT switch. So that is a double pole, double throw switch. So which will be connected to the external resistance. So here we will be considering, so the test, the aim of the test will be to find the stray losses, and finding the stray losses, later we'll be finding the armature copper loss and shunt field copper losses for any particular load to find the efficiency of the motor. So for that, this is the another test called as the retardation test, or we'll be calling it as the rundown test. So now with respect to this test, so generally as usual the motor will be started under normal condition. So when the motor has been started and it is brought to its rated speed, but while conducting this experiment, we will be increasing the speed slightly more than its rated speed, and later the armature will be cut off from the supply. So once the armature has been cut off from the supply, so the armature slow downs and comes to below its rated value. So we will be noting down the time period during cutoff and after some percentage of voltage when it falls down. So that will be noted down by using this voltmeter. So the two different times will be noted for two different positions of the voltages. So that's why the voltmeter has been connected at this particular place. So as we know that as the voltage gets increases, your back EMF also gets increases, or when the voltage starts reducing, back EMF also starts reducing. That we have conducted in the speed control of your DC motor. Okay, so that is the main purpose. So once the armature slow downs, then the kinetic energy which will be coming into consideration. So the kinetic energy which is used to meet the rotational losses. So the kinetic energy of the armature will be represented as half I W square, that is omega square. So where omega is the angular velocity and I is the moment of inertia of the armature. So therefore with respect to this, so we can find what is the rotational losses. So when we go for the rotational losses, so we have to keep in our mind that both mechanical as well as the iron losses will be coming into consideration. There is the friction, windage and iron losses. Suppose if the armature, if there is no excitation with respect to the armature, then only mechanical losses will be taken into consideration. So that is the one note we have to make in this particular experiment. So now with respect to that, so what is the rotational loss? So rotational loss will be equal to, that is W will be considered as the rotational loss, so which will be equal to rate of loss of kinetic energy. So that is the difference with respect to the time. So here the two parameters will be taken into consideration. One, the moment of inertia, and second, the speed comes into consideration. So omega is nothing but 2 pi n by 60. So n again it is a square times. So that comes into consideration. So these two quantities has to be taken into consideration in further slides. So here again, if you see this second diagram, that is the graph. So the graph is being plotted with respect to the torque and the speed. So with respect to the torque and the speed, so to find the difference with respect to this speed, so we have to go for representing the what is the fall of the voltage. So then we can find what is the difference with respect to the speed. So now here you can see the speed which will be rated above the rated speed, and once the armature is been cut down from the supply, so slightly it starts reducing the speed, and it meets at one particular point, that is the point P comes into consideration, where the normal speed which will be occurring in your motor. So now with respect to this, and later the speed starts reducing, and a small curve which will be represented here. So P is the point where the normal speed occurs. So now drawing the line at the normal speed, that is at point P. So let us consider point A and point B. It is drawing a tangent AB on the graph. So now with respect to this, so what is the difference between the speed with respect to the time? So sorry, this is not the top, this is time. So now with respect to the time, so OB is the speed and OA is the time. So now with respect to difference with respect to this speed will be OB, and difference with respect to the time will be OA. Now if you come to the slide, so OB is in RPM and OA is in seconds. So now with respect to this, so what will be the rotational loss? So W is equal to I into omega divided by dW by d omega by dt. So where omega is equal to 2 pi n by 60. So now substituting omega is equal to 2 pi n by 60, so we can represent the rotational loss is equal to 2 pi by 60 square I into n into dn by dt. So differentiating with respect to the speed, so that is a 2 comes into consideration. So now with respect to this, so if I do the differentiation and substituting the values, so rotational loss will be equal to 0.011 in into dn by dt. So please note down this formula with respect to the rotational loss. So this is finding for difference with respect to the speed and with respect to the time. So now let us go for the another two conditions, that is to find the moment of inertia. So moment of inertia will be calculated by considering I and eliminating I. That is in first case we will be calculating I, and in the second case we will be eliminating I. So now in the first case, when we go for starting considering the moment of inertia, so just we will introduce a small flywheel in the shaft of the motor. So first showing down the curve drawn with armature alone. So the flywheel of known moment of inertia I1 is been introduced into the shaft and slowing down the curve once again. So now with respect to this, obviously the time, whatever the getting time to slow down the motor, it takes more time. So with respect to that, we will be getting the two different time period. So that's why for any given speed, dn by dt1 and dn by dt2 are been determined in this particular case. So now with respect to this, if I consider, so what is the equation? So considering this equation, so that is omega is equal to 2 pi by 60 square I n into dn by dt. So that is with respect to 1. So I'll consider with respect to first case as dt1 and second case as dt2. So now in case of first case, w is equal to 2 pi by 60 whole square in into dn by dt1. So this is with respect to the armature when there is no excitation. So second, when I go for the second case, so considering the rotational loss, so introducing the flywheel. So that is I1, if I consider in the equation, so then the second equation will be represented as 2 pi by 60 square into I plus I1 into n into dn by dt2. So now with respect to first case and second case, the rotational losses are same. So with respect to this, equating these two equations, so combining this, so 2 pi by 60 square and here 2 pi by 60 square gets cancelled, and I plus I1 n gets cancelled, I plus I1 into dn by dt2 which will be equal to I into dn by dt1. So now I have to get the expression for moment of inertia I. So to get the moment of inertia I, so just you divide this I in towards the left side. So 1 plus, that is I divided by I will be 1 plus I1 by I into dn by dt2. So I will be equal to dn by I will be equal to I1 into dn by dt2 divided by dn by dt1 minus dn by dt2, difference with respect to time 1 and time 2. So now the moment of inertia I will be equal to I1 into t1 divided by t2 minus t1. So this is the expression for finding the moment of inertia when an additional, that is a flywheel, is being taken into consideration. That is I1 is taken into consideration. Now in the second case where I is been eliminated, so what will happen? So just we'll be considering the 5% difference with respect to the time. So first time taken to slow down, say 5%, not on the armature alone. So that means only with respect to the armature. So now with respect to this, the armature and the time is been taken into consideration. So while using the DPST switch, that is here the DPST switch will be thrown, disconnecting the armature from the circuit, and it will be thrown to the load, that is resistance will be taken into consideration. So when the resistance is being taken into consideration, the additional, that is the loss, new power will be coming into consideration. That power will be considered as W dash, that is V into whatever the voltage and whatever the current which will be flowing here, that is the loss. So V into IA will be taken into consideration. So now with respect to that, so the DPST switch will be cut off. The armature from the supply automatically joins to the resistance. Now when it joins to the resistance, the additional loss comes into consideration. So that is nothing but IA square into RA plus R. So this can be written as V into IA, where V is the average voltage and I is the average current through the resistance. So now this power will be considered as W dash. So here we are introducing I1 in this case, but here we are introducing the additional loss. So when I introduce the additional loss, so W dash be the power, that is this power, V into IA. So now representing the equation, W is equal to 2 pi by 60 square into I into N, that is considering the first equation, dN by dt1. So here the difference, the speed, we are considering it as same. So when I go for the second, W plus, here we are adding the additional power. So W dash, which will be equal to 2 pi by 60 whole square into I into N into dN by dt. So now with respect to this, so if I equate these two equations, dividing the equation 1 and equation 2, so W plus W dash divided by W1 will be equal to dt1 by dt2. So that means considering the same speed, there is no change. So now with respect to that, the rotational loss can be represented as W dash into dt2 by dt, difference with respect to time 1 and time 2. So here W will be equal to the additional power, that is the W dash, which is nothing but V into IA into T2 divided by T1 minus T2. Here the difference with respect to the speed, dN by dt1, is the rate of change of speed without external load. So here this is with respect to the external load when resistance comes into consideration. So this is the expression for the rotational loss when the moment of inertia is not been considered. So please note down these equations so that we can solve the numericals easily. So this is the first equation. So W is equal to 0.011 IN into dN by dt. The second expression will be moment of inertia, that is I is equal to I1 T1 divided by T2 minus T1 when moment of inertia is been taken into consideration. When eliminating moment of inertia, W is equal to W dash into T2 by T1 minus T2. And there is the additional, that is the loss when the resistance comes into consideration. W dash is equal to V into IA. So this method will be applicable for both the shunt motor as well as the generator. So to find the stray losses. Okay. So not only to find the stray losses, so later we can find the efficiency of your DC motor. So that's how we'll be conducting the experiment in our lab. Is there any doubts? Is there any doubts? Any doubts?
No, sir. No, sir.
Okay. So shall we go for the numericals?
So once display the PDF, sir, we will write that formula once.
It has been displayed, no?
I said like little zoom on.
Okay. Is it clear?
Yes, sir. Yes, sir.
So note down this formula for rotational loss. W is equal to W dash into T2 divided by T1 minus T2. This is the one formula. Done. And note down the equation for W also. W is equal to 2 pi by 60 whole square In into dn by dt1, and W plus W dash is equal to 2 pi by 60 whole square into In into dn by dt2. So please make a note, we are not disconnecting the field at any cost. Okay, only the armature will be disconnected from the supply. So field will be always excited. Done. So this is the
Yes,
another
sir.
this is the another additional loss. Additional loss W dash is equal to V into IA or IA square into RA plus R. So this is the another equation when moment of inertia has been taken into consideration by giving additional of flywheel, that is I1.
Thank you, sir.
So now let us go for the numericals. Is it visible? Numericals.
Yes, sir. Yes, sir.
Okay. So in a retardation test on a separately excited motor, the induced EMF in the armature falls from 220 volts to 190 volts. Okay, so this is the two different voltages is giving. So in our lab also will be representing the same. Okay, so getting the motor beyond its rated speed, and later once if we remove the armature from the voltmeter, so during before removing the armature from the supply, what is the voltage, and after some time, so some seconds or some minutes, will not go for minutes, some seconds, if I remove that DPST switch, so what is the fall for some 3 seconds or 4 seconds, what will be the voltage. So that voltage will be noted down. Okay, so that's the average voltage is giving, that is induced EMF of armature falls from 220 volts to 190 volts in 30 seconds on disconnecting the armature from the supply. The same fall takes place in 20 seconds. So this is the second time he is giving. The same fall takes place in 20 seconds if immediately after disconnecting armature is connected to a resistance. So after disconnecting from the supply, once if you put the DPST switch towards the resistance, okay, so that time it is 20 seconds. So what is the stray loss of the motor? So the average current is giving as 10 amps. Okay, so can you able to find what is the solution of stray loss? So stray loss is nothing but the value of W. So W is equal to W dash into T1 minus divided by T1 minus T2. Can you able to find what is the rotation stray loss? It's a direct formula. So W dash is equal to V into IA. So V is nothing but you have to take the average value. Okay, so 220 plus 190 divided by 2. So that gives you the average value of your voltage. So 220 plus 190 divided by 2 will be getting around 190, 195. So to find W dash, are you getting average voltage? So 200 plus 190
205, sir. 205, bro.
divided by 2. 195 you are
205, bro.
getting average voltage.
205, sir.
You must take average. 220,
Two
Sir,
not five.
205. 205, bro.
205.
205.
Yes,
Okay,
Yes,
sir.
sir.
220 minus 190. Okay, so
W dash is
205.
2050.
W dash.
2050.
Okay, so W dash is equal to product of voltage and the armature current. The armature current is given as 10 amps.
Yes, sir.
Okay, fine.
Stray loss is 4100.
4100.
00.
Okay, so T2 is 20 seconds. T1 is 30. 30 minus 20. So how much you getting stray loss? 4,100.
4,100, yeah.
Yes, sir.
Okay, so must get stray loss as 4,100. Okay, so let us, shall I go for next numerical?
Yes, sir.
Sir.
When I go for second one, in a retardation test on a DC motor with its field normally excited, the speed falls from 1525 to 1475 RPM in 25 seconds. So now he is giving the speed, difference in the speed in 25 seconds time he is giving with an average load of, so load he is giving as 1 kilowatt supplied by the armature. The same speed drop occurs in 20 seconds. Find out the moment of inertia of the rotating part in kg meter square. So now we have to find the moment of inertia. So now to find the moment of inertia, so what is the formula which has to be taken into consideration? So that is I is equal to I1 into T2 divided by T minus T2. Right? So note down the two speeds. So for the next numerical, we have to find what is the moment of inertia. So to find the moment of inertia, so go for W dash formula, that is 2 pi by 60 whole square into In into dn by dt. And also W is equal to W dash into T2 divided by T1 minus T2. So W dash is giving as 1 kilowatt. So T1 is 25 seconds, T2 is 20 seconds. So find what is the rotational loss. After finding the rotational loss, so substitute W dash is equal to 2 pi by 60 square In into dn by dt.
Sir, N, which one you have to take?
Pardon?
N, speed, which one you have to take, sir?
Speed, it is the average speed. So always here, whatever the two different speeds if it gives, you have to go for the average. What is the normal speed? Average speed. It is 1500, right? For any DC motor. Only for AC motors, it will be less than 1500. But here, the average speed of a DC motor will be 1500. So difference in the speed will be whatever the data he is giving. 1525 minus 1475. Are you getting? Or shall I go for presenting some other slide? I cannot stop this. So PPT is coming, right?
Yes, sir.
Yes, sir.
Okay, so I'll go for the presentation, which formula you have to take into consideration. So here, as per the numerical, okay, so this is the what he is giving with respect to the time. So W is equal to 2 pi by 60 whole square into In into dn by dt1. Okay, are you getting? So here N is the average speed. Average speed is 1500 RPM. So W is giving us 1 kilowatt. Fine. So now with respect to this, find what is the value of I. So now with respect to this, if I want to find what is the difference in the speed. So difference in the speed is giving us 1525 minus 1475. So that is the difference in the speed. So from here, you find what is the value of rotational loss. That is W is equal to W dash into T2 divided by T1 minus T2. And find what is the W.
4.
Pardon?
W is 4.
W is
4 kilowatt.
W is 4 kilowatts.
I is 0.12, sir.
0.12.
Yes, sir.
It is in gram or it is in kg. Gram meter square or kg meter square.
1
I think
second.
it is. I
I
think it is
think
gram meter square. So kg multiplied by 1000, you will be getting it as 121.8 kg meter square.
yes, sir. 121.21, sir.
Yeah, 121.21. So I'll go for the third numerical and I'll stop for today's class. And the last numerical, we have to go for some assumptions. Okay. So there is no excitation. When there is a full excitation, so it has to be explained clearly. So that I'll do it tomorrow and I'll start to model 4. So model 4 is totally a theoretical. Only some numericals will be come into consideration. It is speed control as well as the starters. Starters for a three-phase induction motor and single-phase induction motor will be taking into consideration in model 4. Okay, so that we'll see tomorrow. Okay, third numerical, I think I did not copy properly. The same second has been taken into consideration. Able to see the numerical for the editing I'm doing? Excuse me. Can you see the third numerical?
Yes, sir.
Is it clear?
Sir, can you zoom it, sir?
Yeah. Is it clear?
Yes, sir, it's clear.
Now in this thing, so we have to find what is the efficiency of your DC motor. Okay, so he is giving the data stating that the average voltage is given. A retardation test is made on a separately excited DC machine as a motor. The induced voltage falls from 240 to 225 volts in 25 seconds on opening the armature circuits and 6 seconds on suddenly changing the armature connection from supply to the load resistance. So T1 is giving, T2 is giving, and average current is giving. So find the efficiency of the machine when running as a motor and taking a current of 25 amps on a supply of 250 volts. The resistance of its armature is 0.4 and that of its field winding is 250 ohms. Okay, so here we have to find what is the stray losses. So to find the stray losses, we have to find what is the shunt field copper loss and armature copper loss. So what is the, so he is giving taking a current of 25 amps. So what is the armature current? So that we have to take into excuse me, into consideration. Okay, and okay, so based on this, find what is the efficiency. Can you able to solve? So what is the formula to be used? Can you able to find the efficiency? So just I'll give the hint. Okay. So first find the average voltage. So average current he has given. Go for W dash. So T1 he has given, T2 he has given. So find what is the stray loss. So stray loss is equal to W dash into T2 divided by T1 minus T2. So after finding this stray loss, input
74.
current was pardon?
Sir, to find W dash average, we have to consider, sir.
Average voltage you have to consider. That is 240 minus 225.
Stray loss is 734.21.
Stray loss W dash is equal to V into IA. So V is 240 minus 220. 240 plus 225, that divided by 2.
230.
So 232.5 is your average voltage into 10 is your current. So W dash is equal to 2.325 kilowatts. Right? Into T2 is 6 seconds. Divided by 25 minus 6, it is 19. So stray loss will be getting the 734.2 watts. Is it right? Are you getting stray loss 734.21 watts?
Yes, sir.
Okay. So once if you know the stray loss, now he is giving the total current. Fine. So total current is 25 amps. Supply voltage is 250 volts. Armature resistance is 0.4 ohms and field resistance is 250 ohms. So field current will be 1 amp. So 25 minus 1 will be 24. So 24 amps will be your armature current. So now find what is the armature copper loss and shunt field copper loss.
Armature copper loss is 231.74 watts.
Okay, so that is 24 square, right? 24 square into 0.4.
0.4.
Yeah, 230.4 watts is your armature copper loss. Shunt field copper loss?
216.225.
216.225. So stray loss, add the stray loss. So that gives you the total loss. So stray loss plus armature copper loss and shunt field copper loss will be your total loss. So what is the input here? So input is 25, current is 25 amps into 250 volts. So 6,006.25 is your input. So if you go for minus losses, so you'll be getting the output. So what is the efficiency?
81.1, sir.
Yeah. So 81.1 is your efficiency. Everyone are getting? Everyone are getting efficiency? Everyone are getting efficiency as 81%.
Yes, sir.
Okay, so
81.1.
fine. Go, uh, 81 point. Okay, I'll go for the last numerical. So just I'll give the hint. So you can go according to that, or I'll explain. Let us see it tomorrow. So here the retardation test is carried out on 1000 RPM DC machine. The time taken for the speed to fall from 1030 RPM to 970 RPM is 36 seconds with no excitation. So with no excitation means, so here the armature has no excitation. So only mechanical losses will be taken into consideration. So with the full excitation, so here the armature comes into consideration. Next, 9 seconds with the full excitation and the armature supply an extra load of 10 amps at 290 volts. So that means the armature with the resistance value has to be taken into consideration. That is in case C. So then we have to find what is the moment of inertia. So mechanical loss at mean speed of 1000 RPM and iron loss. So these are the three cases we have to find with respect to your retardation test. So that's the hint what I have wanted to give. In first case, please remember, so while armature is slowing down, there is no excitation. So kinetic energy will be considered for only for mechanical losses. So not for electrical, that is magnetic loss. There is no iron loss. In second case, both mechanical as well as iron loss comes into consideration. So then we have to find what is the stray loss. That is stray loss will be known. And last, so the moment of inertia has to be taken into consideration. So that is the formulas which has to be used will be 2 pi by 60 whole square in into dn by what is the second form numerical we have solved. So we have to go according to that. So with respect to difference in the speed he has given, sorry, with respect to time, we have to consider that time t1 and t2, and we have to solve the numerical. So try to solve. If you are not getting, so let us see in the tomorrow's class. Okay. Shall we come out of the class? Thank you all.
Thank you, sir.
Thank you, sir.
Thank you, sir.